Welcome all of you, and last one or two classes we have been discussing about one of the internal interaction parameters, that is scalar coupling. I discussed a lot about the features of scalar coupling, especially some of the important parameters, important things we must remember. For example, scalar coupling is a covalent bond mediated coupling, and it is just a number. It can be positive, negative or 0. And also I said when one spin is coupled to another spin through covalent bond mediated coupling, then there will be a multiplicity of the transition, which comes because of one spin sees the other spin in different possible orientations. When I took the example of two spins, I said if I have a spin A, it can couple to spin X which has two spin orientations alpha and beta. As a consequence, spin A will see spin X in either alpha and beta states and split into two energy states. Similarly, X will see A in two energy states and give rise to 4 transitions. And of course, I also said the sign of the coupling could be positive, negative or 0. And the sign of this coupling has no bearing as far as the appearance of the spectrum is concerned. I said when I have a positive sign, let us say two spins coupled will give 4 lines. When it is negative sign of the coupling, it is just transition appears reverse, that is all. As far as the total appearance of the spectrum is concerned, there is no effect at all. And I further continued and explained about multiplicity pattern that we are going to get. When one spin is coupled to chemically inequal different spins, then by applying the family tree approach, I said when one spin coupled to n spins, 2 to the power of n possible transitions are there. For example, one spin is coupled to 3 spins, it will become 8 lines, it gives rise to 8 lines. And if there are 4 spins like that, 8 into 4 there will be 32 transitions, that is what I said. When we have groups of equivalent spins, we get into what is called 2ni plus 1 rule, in which number of transitions that we can get when one spin is coupled to chemically equivalent other spins, how many transitions we are going to get, that also we discussed. And I said intensity of the transitions when among the group of chemically equivalent spins coupled is given by what is called a Pascal triangle, that is what I said. Pascal triangle is also nothing but coefficients of the binomial expansion, that is what I showed. And then we took several examples to show how the spectrum comes if let us say CH is coupled to CH2, CH3 etc. And I arrived at different multiplicity pattern like pentates, sextet, septet etc. varieties of multiplicity pattern. When what happens when one proton is coupled to 2 different protons with different couplings also we worked out. We continue further with that discussion today, and I want to show you what will happen to the splitting of a particular proton or group of protons when it is coupled to several other spins. It could be single spin or multiple spin which are chemically equivalent. In which case, how do we get the multiplicity pattern and what is the nomenclature adapted for that we are going to discuss today. For example, I will consider a CH proton here which is marked here, which is split let us say by CH and CH2. Now the question is, we have to put some condition about the coupling here. What is the strength of the coupling? If A is coupled to Y, A is also coupled to X, because I am looking at A. Of course, I can look at X and Y also, that is a different question, but I am looking at A has a coupling with Y and also with the X, and I put a condition AY is greater than AX. That means the coupling between A and Y, JAY is greater than JAX, in which case what is the type of splitting we are going to see? We will see that. For example, the CH proton when it is coupled to CH proton, another proton Y, A is coupled to Y. Because I said AY is larger, first it is a single proton gives us to a doublet, and the doublet separation corresponds to JAY coupling. Okay, this one proton splits into 2 lines of equal intensity 50-50, half of intensity. Okay. Now further what happens, this also splits into triplet, each line of the doublet will become triplet because of coupling with 2 chemically equivalent protons CH2. As a consequence, it is going to be doublet of triplet. This pattern is called doublet of triplets, and this triplet separation consecutive lines of the triplet gives the coupling between A and X. and this center of this triplet to center of this triplet separation if you measure, you are going to get the coupling between A and Y. This is a condition I have taken. AY coupling is larger than AX coupling. The splitting pattern for A appears to be what is called doublet of triplets. Remember, this is because the triplet coupling is smaller. Always when you are putting the nomenclature like this, we have to mention the largest coupling first. First largest coupling is doublet, that strength is larger, and then each line is split further into triplets. So, this nomenclature, remember how do you mention this nomenclature? It is called doublet of triplets, okay, and the center of this correspond to chemical shift of this proton A. Okay. Now, what is this pattern for Y? I was looking at A proton earlier. Now, I look for Y proton now. What will happen? Remember the same condition I have put, AY is larger than AX. What will happen? AY is again a doublet. Because of coupling, AY is larger, it is a doublet, and each line of this doublet is further split into triplet. This triplet comes because of coupling of Y with X, and YX coupling is smaller because it is separated by several bonds. I have deliberately taken AY is larger than AXY. Previous case it was AX, and this YX is even larger than AY. AY is even larger than XY. As a consequence, again the pattern you are going to see is doublet of triplets, and only thing is the appearance of this pattern remains same. The triplet separation is smaller, that is all, because the coupling Y and X, JYX is smaller compared to JX in the previous example. Again this pattern is called doublet of triplets because the larger coupling is a doublet. Okay. We will go further. In the same molecule now I am going to see X proton. What will happen now? Let us put a condition, JAX is larger than JYX or XY. YX and XY both are same because interaction NMR is same, both always mutual. Now, what is the pattern we expect? JAX is larger, A spin will split this into a doublet because CH3 proton see A in the only two possible orientations. It will be a doublet, but it also sees Y proton, again it is a single proton. Then what will happen? Each line of this doublet is going to be further split into another doublet, and this separation correspond to AX coupling, larger doublet, and each line is split into another doublet, the smaller doublet correspond to YX coupling. So, what do you call this pattern? Of course, center of this is nothing but chemical sheet of this X. So, what is this pattern called? This is again called doublet of doublets. Remember the pattern, when we observed A, it was doublet of triplets. When I observed Y, it was doublet of triplets. But whereas I am observing X here, the pattern is doublet of doublets. This larger separation from any of the line of doublet to other line of this doublet is exactly identical line. If you take the rightmost line here and take rightmost line of this doublet and measure the separation, that gives AX, which exactly correspond to this, because the second splitting of the doublet is from the center of this an equidistance. There will be two lines each, one line each for this side and one line from this side. So, that means you are going to get a doublet exactly centered at this peak. So, that means you can measure from this peak to this or this peak to this, does not matter, it gives JAX coupling. Measure the separation, it gives you JXY coupling. This is what is called doublet of doublets. So, now I will consider a situation, JAX is larger than AY, this is larger than AY. Then what is the condition? When AX is larger, I am looking at A now. Remember, earlier I was considering a different situation, AY was larger than AX I took. And now a hypothetical example, I am taking AX larger than AY. So, A will split into a triplet because of this two equivalent protons, it is a triplet, and separation between two adjacent lines of the triplet gives you coupling between the proton X and proton A, and center always correspond to chemical shift of X. Fine. Now, each line of this triplet is further split into a doublet because of proton Y, and this doublet separation is JYX. Okay. So, this is the situation we are going to consider. I am sorry, this is AX, no, this is AX, and this separation correspond to AY, because I am looking for A, correct, AY, this is AY coupling. So, this is A is split into triplet because of this, each of the triplet is split into doublet because of AY coupling, and this is the pattern you are going to get. This is the AY separation, and any line of this triplet you take from leftmost line to this one, or from this to this, or this to this, or this to this you take, it gives rise to AX coupling. What do we call this triplet? The larger coupling here is triplet, smaller coupling is doublet. So, it is called triplet of doublets, and this is the pattern we call triplet of doublets, and the center of this multiplicity pattern correspond to chemical shift of proton A. That is what it is. Okay. Let us continue further. We will take few more examples. Now, I am considering single proton coupled to CH and CH3 protons. What will happen? Extend the logic. Now, we are looking at proton A. I am putting a condition AY is larger than AX. Like in the previous example, let us extend the logic. A, because of coupling with proton Y, it has to be a doublet, because that coupling is larger, it is a doublet, and each line of the doublet is split because of 3 equivalent protons, CH3 group. 3 are chemically and magnetically equivalent protons, makes each of these line into a quadret. What do we call this pattern? The larger separation is doublet and smaller separation is quadret. So, this pattern is called doublet of quadrets. Again, center of this multiplicity correspond to chemical shift of A, which I am seeing, and take any two adjacent lines of the quadret, that gives you coupling between A and X, and any line, similar lines you take leftmost to leftmost here, this line to this line, second, third line to third line, fourth line to fourth line, if you consider between the quadrets, measure the separation that correspond to JAY. So, this pattern is called doublet of quadrets. What happened to the splitting pattern? AX is larger than AY. Here this is larger. Earlier case I took the example, AY is larger, doublet was larger, doublet coupling. Now, I am considering quartet coupling is larger. What is going to happen? The proton A is split into quartet because of CH3 protons, all the 3 protons are equivalent, it will become a quartet. Of course, by the Pascal triangle we have already understood the intensity ratio is 1:3:3:1, it is a quartet. So, A will become a quartet because of this, and then what will happen? A is also coupled to proton H, this Y, this proton, this Y proton it is coupled to. Then what is going to happen? There is a single proton. When it is coupled to single proton, each line of this quartet is going to become a doublet. This is how the pattern comes now. And this separation, any adjacent line if you consider, it gives a coupling between A and X. And now, in this case, coupling between any of these two lines of the quartet, if you consider adjacent lines of this quartet, this gives rise to AY coupling, and from center of this to this, or this to this, or this to this, whatever you consider, that gives rise to AX coupling. So, this is how it is, and the center of this multiplicity correspond to chemical shift of A. What do we call this pattern? This pattern is called, largest coupling is a quartet, so it is called quartet of doublets. Remember, earlier it was doublet of quartets, but now it is quartet of doublets. So, you have to find out which strength is larger, which coupling is larger, that should be named first. In this case, quartet is coupling is larger, so we call it as quartet of doublets. Now, consider this situation, same A proton I am considering, instead of CH I made it CH2. What is the pattern we expect? Very easy to understand. When, since I again put a condition, this is larger than this coupling JAY is larger than AX, that is the condition I have put. So, what is the pattern we are going to get? A will split because of CH2 protons into a triplet. Of course, you can take CH3 coupling also first. I told you in the previous class. The order in which you take the coupling to generate the multiplicity does not matter. Order remains invariant. Whether you take this coupling to this first or coupling of this to this does not matter. You can take this first, take this second, or you take this first and take this second, pattern remains same. So, does not matter. We will consider first coupling of this proton A with proton Y, which is CH2 proton. What is the pattern we get? This is a CH2 proton, it will split this into a triplet of the intensity ratio 1:2:1. Further, this proton is also coupled to CH3 group. There are 3 protons equivalent. So, what is the pattern we expect? Each lane of this triplet is going to be split into quartet because of this. So, now the pattern we are going to get is this. This larger separation correspond to AY coupling, and in the quartet take the adjacent lanes of this quartet, that gives rise to AX coupling. So, any lane of this quartet to this or this to this, this to this or this to this you consider, this gives rise to AY coupling. If you see this we measure AY coupling very easily, but actually this is not the only thing, we have other couplings also. So, when the pattern comes like this, you should know how to measure the coupling. So, this is center of this gives you chemical shift, and this separation gives you AY coupling. Any peak of this quartet you consider, identical peak in the other quartet you consider, like the leftmost peak to leftmost peak, second peak to second, third to third, fourth to fourth. Similarly, this group to this group you consider in the same manner, that separation gives you AY coupling. So, you understood how do you measure coupling from this multiplicity pattern. And then what do you call this pattern? This is called triplet of quartets. Remember, doublet of doublet, doublet of triplet, triplet of doublet, triplet of quartet, everything we have understood now. This is the situation now. Now, I have put AX coupling is larger. See, these are all subtle points. You should understand the multiplicity. To understand and explain the multiplicity pattern, you must know how the coupling, which coupling is larger, how the splitting pattern arises depending upon the coupling. I have put a condition, this coupling is larger now, AX is larger than AY. Previous example, CH2 coupling with proton was larger. So, this is going to be a quartet now. First coupling is large quartet I have taken, and each lane of the quartet, of course, adjacent lines gives you AX coupling, center of this gives you chemical shift of A. Each lane of this quartet is split because of this Y proton CH2 into a triplet. This is 1,3,3,1 intensity and this is 1,2,1 intensity. So, each lane of the triplet quartet will be a triplet, and this separation gives you coupling between A and Y, and this separation to this separation, this to this, this to this, whatever the order you take, you take any of the multi-triplet, and then exactly identical lines you have to identify. If it is the rightmost line, take the rightmost line here. If the middle line here, take the middle line. If the leftmost, take the leftmost line, and measure the separation between them, that correspond to AX coupling. And between the multiplicity triplet, if you measure the separation between adjacent lines, that gives rise to AX coupling. So, this pattern is called quartets of triplets, quartet of triplets. Okay. Center will give you coupling. Instead of CH2, I will make CH3 now. Obviously, we can extend the logic, very easy. Whatever the pattern you take, whether this is larger or this is larger, does not matter. So, if I consider, of course, this is some X or something which is not coupled to. I have named this proton as Y. This is another substituent, nothing to do with proton. Okay. Now, Y means it is some other substituent. When A is coupled to any one of this proton, I have taken AY to be larger, does not matter. You can take AX also first splitting, it will be a quartet. Because both are CH3 group, does not matter, you can take whatever you want. I have taken this and it is a quartet, and each line of this quartet is further split into quartet because of this CH3 group. There are 2 CH3 protons coupled to a single proton with different coupling strengths. As a consequence, it is going to be quartet of quartets. This is what you are going to get. Of course, similarly you can measure any of these line you consider, identical as other quartet you consider, measure the separation, this gives you AY coupling, and measure the adjacent lanes of the quartet, that gives you AX coupling. So, this is called quartets of quartet, and you can get the coupling information, and the center of the multiplicity is chemical shift. Okay. So, these are the common first order splittings we always get when we are looking at different protons coupled among different groups. It could different protons, could be a single proton or a group of protons. Simple example of a molecule like this, all 3 independent protons are there. There is no CH2 group, no CH3 group. All are coupled among themselves, let us say this A is coupled to X, A is coupled to M, X is coupled to M, X is coupled to A, M is coupled to X, and M is coupled to A. I already explained to you, when one proton is coupled to other protons, each line is going to, each particular that spin gives rise to 4 peaks. Okay, first it will become a doublet, and each line of the doublet become further doublet because of this coupling with M. So, A will be 4 line pattern. Similarly, X will be 4 line pattern and M will be 4 line pattern. Patterns, identical intensities will be there, but the separations of the multiplicity, different peaks are different because the couplings are different. So, A will give rise to 4 peaks, A experiences coupling with AX and AM, X gives 4 peaks, A gives X and experiences coupling with A and M experiences coupling with A and X. We get 4 peaks. Each proton will be what is called doublet of a doublet. Each group of protons gives rise to doublet of a doublet, and intensity pattern is very easy, 1:1:1:1. So, one proton is coupled to more other protons, single protons, several other individual protons. This is the pattern we always expect, but always remember the order of coupling is immaterial, but the strength of the coupling matters a lot, which is larger. Now, I am considering A. I have put the condition AM is larger than AX, larger than AY. One proton is coupled to 3 other individual protons. An hypothetical molecule I am considering, looking at proton A, the spectrum of proton A. Now, first it will split into M, split because of M into a doublet. This separation corresponds to AM. Now, I will bring the coupling of this with X. Then each line of this doublet is going to be a further split into a doublet. We already worked out long back, 1 or 2 classes back, how in the familiarity approach it comes. Again, each line of this is going to be further split into doublet of doublet of doublet. This is called TDD, doublet of doublet of doublet. This is a nomenclature used in NMR. So, A will become 8 line pattern. Similarly, X will become 8, Y will become 8, and M will become 8 depending upon the coupling strengths. Okay, this is how it is. This pattern is called doublet of a doublet. And if I have again multiplicity pattern, because of chemical equivalent proton, now instead of 1 or 2 protons, I am considering multiplicity, groups of 2 or 3 protons coupled to single one. A is coupled to this one, X, M and Y. Very easily you can understand the logic. A, I have taken AM coupling larger, large coupling is doublet. Then it is split into triplet, each line of the doublet split into triplet because of Y proton, and each line of this triplet of triplet is further split into triplet of triplets because of coupling with other CH2 proton. One, for example, you understand this logic. This is the AM coupling, first doublet, and each line of the doublet is split into a triplet. This is AX AY coupling. There are 2 triplets. Any adjacent line of the triplet, if you consider, you are going to get AY coupling. Further, what will happen? It is split because of X2 protons. Each line is going to be a triplet now. Triplet, 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 triplet. See what is happening? You are going to get a very, very complex pattern. Not easy to analyze. But since I knew where I have started with, this center is considered to be the chemical shift of A, and this pattern is called, this pattern is called doublet is the largest coupling, then second largest coupling is a triplet, and another smallest coupling is also a triplet. This pattern is called doublet of triplets of triplets. This is the nomenclature we have to use. So, you can use this. What happens if you take the other coupling larger? Instead of doublet, for example, this coupling if it is larger, first it is going to be triplet, and each line of the triplet is split into a doublet because of M, and each line of the doublet is further split into triplet because of other coupling. Then what do we call this pattern? First is a triplet, it is triplet of doublets. Now it is triplet of doublets of triplets. This is what the nomenclature you have to use. It is called triplet of doublets of triplets. As always I said, this separation gives you AS coupling, and identify the particular pattern. If you go by the family tree, this separation gives you AM, and center of this to any of these lines if you consider will give you AY coupling. So, like this you can analyze and get the coupling information, but the pattern what you have to identify is important. This is called triplet of doublets of triplets. This is even more complex. Identical molecule, I am only changing the groups here. CH became CH2, again now it became CH3 here. What is the pattern you expect? A is going to be a triplet because of coupling with Y, large triplet. I have written coupling strength larger, AY is larger. Then each line of this triplet is going to be further split into a triplet because of M. You get 2 triplets, I am sorry 3 triplets you got. What is going to happen now further? This is also split because of CH3 group. So, it is already triplet, it is triplet of triplet. Each line of the triplet is further split into what is called a quartet now. You are going to get one quartet, another quartet, another quartet, another quartet. See, so many quartets you are going to get. What do you call this pattern? You see the spectral complexity, remember it is not easy to analyze. It takes enormous amount of experience required to analyze such a spectrum. Nevertheless, since I know the coupling pattern, I know the molecule, what do you call this pattern? This is called triplet of a quartet. This is called triplet of triplets of quartets. So, basically remember, if you consider the splitting pattern at the active site of any proton coupled to other groups of protons, normal abbreviation what we use in NMR is DD, means doublet of doublet. When you say doublet of doublet, largest coupling is a doublet, second largest coupling, in this case there are only 2, is it also a doublet. If I consider DT as the nomenclature I use for the pattern, first is the largest coupling is a doublet, second coupling is a triplet. Instead of DT I write TD, that means first largest coupling is a triplet, second coupling is a doublet, smaller coupling is doublet, largest coupling is triplet. Like that you can say quartet of triplet, first largest strength is quartet, then the smallest strength is a triplet. You can have many couplings like I showed you, 2 or 3 coupled to each other, you can have DDQ. That means first coupling is also a largest coupling is doublet, second largest coupling is also a doublet, and third is a quartet. So, that means one proton is coupled another proton gives you a doublet. It is coupled another single proton gives you another doublet, each line of doublet will become doublet. Then it is also coupled to CH3, then doublet of doublet becomes each line of this doublet of doublet splits into quartet, and largest coupling is first doublet, then second doublet, the smallest coupling is quartet, we call it DDQ. Like that TDQ, triplet of doublets of quartet, first coupling is triplet largest, then second coupling is doublet, and the least coupled one is quartet. This is the nomenclature we use for analyzing any NMR spectrum of any molecule when there is multiplicity because of couplings. That we should remember. Okay. So, now I think you have already got an idea how we can identify the multiplicity pattern, etc. So, what I am going to do is I will show some exercises to identify the multiplicity pattern. Since I think the time is getting over already, now time is up, what I will do is I will stop here. In the next class I will take some of the examples to make you more comfortable to interpret the multiplicity pattern, and then we go into few other things, extend this coupling further, and I would like to finish it, and then we will go to interpretation of the NMR spectra and how do you get the Popel nomenclature, everything. So, what I was trying to tell you is, extending from yesterday's discussion, I wanted to show you how when one proton is there, a single CH proton or CH2 proton or CH3 proton, when it is coupled to other 2 protons or other groups of protons of different coupling strengths, what is the pattern we are going to get. I showed we get doublet of doublet, doublet of triplet, triplet of triplet, all varieties of combinations. But how did you arrive at this nomenclature? What is the difference between DQ and QD? dq means first strength is larger, that is doublet, that it is coupled to a single proton, becomes a doublet. Then each line of the doublet becomes a quartet, that is called doublet of quartets. On the other hand, if the coupling strength with respect to Ca3 is larger, quartet is larger strength, it will become a quartet, and then each line of the quartet splits into a doublet. Because of the smaller coupling strength, we call it as quartet of doublet. Like that, we have not only 2, we can have many coupled, one proton can couple to not 2, 3 coupled, 3 protons, 4 groups of protons, 3 groups of protons, like that n groups of protons. Accordingly, the nomenclature is given as DDQ, DQ, DQ, QD, QTD, TDQ, varieties of combinations we can think of. So, I will give, to make you more comfortable, what I am going to do is in the next class I will give some of these examples, then we will go ahead further with the other strengths of the coupling and what in different molecules, and some discuss about Corpus equations, how do we use coupling strength to arrive at the conformation of the molecules, etc. So, we will see how we go ahead further. So, probably with that I will put an end to, because there is no end for this type of NMR is a huge ocean, I can keep discussing this for any length of time. So, we will maybe in the next class we will put an end to this scalar coupling and then go into the interpretation of the NMR spectrum, both proton and X nuclei, etc. So, thank you very much, I am going to stop here.